All right, so thank you for joining this session. So today we're going to talk about physical AI, but in particular, we're going to talk about how physical AI can be deployed in production, meaning not just on a nice demo booth at a trade show, but in production. So quick introduction, I'm Simon. I lead the commercial team at Intrinsic. And today I have my colleagues Christoph and Henrike with me. And we'll walk you through some of the basic principles of physical AI. And we'll also give some real examples about where we've deployed that physical AI on the factory floor in real and customer environments. So I'm going to start with a statement. And that statement is, there's a lot of energy, there's a lot of technology arising. But today, if you go to real factories, what you realize is the number of robots in production is still today a tiny fraction of what it should be. So here's an example. It's the example of CNC machine tending. A CNC machine is a perfect candidate to have automation, putting a robot in front of it. And what you realize is that today, in 2026, for 100 CNC machines that are shipped every year, only 12 of them have a robot in front of them. So the penetration of automation is only still today very, very slow. And so today we're going to talk about why. How come it's such a small proportion of robots on the factory floor? How physical AI can help fix that? And we're going to give some real-world example. Okay, so first thing, why so few robots? Well, for a lot of machine shops or factories, when they produce large batches, a lot of that production, yes, has been automated, but a lot of that has been sent to Asia decades ago. So a lot of what is left in Western Europe or US is actually short batches, this famous high-mix, low-volume that you've all heard about before. And to do high-mix, low-volume, by definition, you need to reprogram your robot very frequently. And a lot of machine shops or factories don't have the robotics expertise to do that reprogramming every week, every day. And even if they did, it would cost a lot of money. So that's the first thing. And second thing, today, because we lack enough technology, a lot of the automation is still based on fixturing. So if you want to introduce new parts every week, every day, you have to recreate some grids, some fixturing, and that costs money. So these are the type of frictions that we see today that prevent for more robotic from being installed on the shop floor. So let's talk about physical AI. Maybe to level set, what do we mean by physical AI? So you've heard a lot in the last 2 years about AI in general, but a lot of the AI you've heard about was actually digital AI. What is digital AI? It's an AI that outputs something that's digital. That can be a text, a picture, a video, a code, an agentic task. So these are the OpenAI, Anthropic, and Google Gemini of the world. And these are based on some foundational technologies like large language models, vision language models. Now, physical AI is different. It is actually more complex. What it does is that it outputs a physical action in the real world, not just something digital. So for example, in the case of robotics, it outputs robotics action, joint movements. And it does that based on foundation models or what we call VLA, which is vision language, but also actions, right? So it is a different class of AI. And we would argue it's the harder class of AI, right? It's not as mature and as deployed as the digital AI that you've all heard about in the last 2 years. Okay, let's get one click down, robots. So fundamentally, a robot does 4 things. It perceives its environment, usually based on some machine vision system. It grasps a part, it moves it, and then it inserts it, right? These 4 base skills cover actually a lot of the applications that you find today in robotics. So let's see how we can infuse a lot of physical AI across these 4 steps. So the first step is perception. And you want to make it so easy that you just upload a CAD and that's it. You don't have to fine-tune a camera. You don't have to deal with complex interfaces. You upload a CAD, and the object is detected. If you do that, by the way, you can move away from fixturing. You can just place your parts on a tabletop. You don't need to have precise grids, precise fixtures, so it unlocks a lot of flexibility. So, for example, at Intrinsic, we have built this intrinsic vision model, which is a best-in-class vision model, which works. You just input a CAD, and out of this CAD, you can generate a lot of cool things like segmentation, pose estimation, point cloud. You can do tracking, bounding boxes, and all of that. So that's perception. That's the first step. Second step, the grasping. Today, traditional automation, you have a guy come with a teach pendant and manually annotate a grasping point for every new piece that you need to handle. Of course, that creates a lot of friction. So you want some skills where same story. You just input the CAD of the parts, and you want the AI to automatically generate the grasp points. First step, the motion planning. Traditional way, you take a teach pendant and you manually teach hard-coded waypoints. That's very painful. It takes time, and that's not conducive to high mix. With physical AI today, you can have a view of your digital twin. You prescribe the starting point, the end point, and all the motion in between is automatically computed in a collision avoidance mode. And now, fourth thing, the last one, once you've detected, grasped it, moved it, usually you want to insert it. That can be cable insertion, that can be inserting a part into the work holding of a CNC machine. Same thing, you don't want to have to explicitly manually program the insertion, the force, the orientation, time with the clamp and so on. So you want to have a skill that just based on the CAD, on the digital twin of the model, we do all that for you automatically. So when you put these four things together, if across these 4 blocks, you automate the programming of that, what you end up with is a system in which whenever a part changes, you don't need to have a human programmer come again. And what that means now, yeah, that's it, you're high mix. You open the door to production floor where you can change your batches very frequently at no cost and no friction. So that's the base technology, that's the physical AI skills. Now this is great, but a lot of the typical stack today, let's say Fanuc RoboKite, KUKA visual components, a lot of these legacy softwares, they haven't been built from the get-go to embed this type of physical AI skills in your design. So now that you bring these new physical AI skills, you also need to, you cannot stop there. You also need to bring together additional layers. The first layer you need to bring is a developer environment where you'll be able to easily design your new now smart high mix application. So a way to easily embed these physical AI skills. And then once you've done that, that's great pre-commissioning, you've defined your application. You also need now a purpose-made stack to deliver this AI post-commissioning on an ongoing basis in production. Again, it is a very different logic from the typical SAT, FAT, if it ain't broken, don't touch it, logic that we had with traditional automation. Now we're talking about applications that evolve continuously post-commissioning, and so you need also this OS and infra for AI, purpose-built for that.
Yeah, please do.
So if you put these 3 things together, new skills, new developer environment, new OS, I'm pretty sure you've heard this type of story before.
Thank you.
Maybe 20 years ago, you've heard a story in the smartphone industry. And 20 years ago, our parent company, Google, pioneered Android. And Android at the time was a revolution because it enabled developers to easily create smartphone applications. Well, that type of full stack is required now for robotics. It happens 20 years later because robotics is notoriously harder than smartphone applications.
Yeah, I know.
But it is a similar logic. And our parent company, Google, actually sees us as would like us to become the Android of robotics, and they approve of that naming. They think it's a good comparison. So we joined Google 3 months ago, precisely to develop that. Maybe to go a little bit deeper into the comparison, what in the smartphone world was the equivalent of some nice apps like Google Maps, now these are these physical skills that I talked about, right? These are the salient points that enable you to create value. The developer environment that we bring with Intrinsic is the equivalent of Android Studio. The OS and infra for AI is the equivalent of Android OS. What for Android is smartphone agnosticity, the ability to program an app that will go seamlessly on an HTC, a Samsung, or whatever. In our case, the equivalent is robot agnosticity. You want to program a KUKA, a FANUC, an ABB, a UR exactly the same way without having to redo your code. And finally, at the end of the day, that's the most important, the community of developers that you have. With Android, you have millions of Android developers around the world who are familiar with the language, with the tools. At Intrinsic, we're starting to create a similar community that's based on some open source tool, but also will gradually speak the Intrinsic language with the goal of being the ones who create these applications that then gets deployed in the real world. Okay, I see there's a lot of people taking pictures of that slide. I'm glad it resonates. Okay, everyone was able to take the picture? Good. All right. So very quickly on our go-to-market, our goal at Intrinsic is really to empower the full ecosystem, the full industry, and to democratize access to robotics. So to do that, we don't want to be the one deploying the robots because we couldn't scale fast enough. So our goal is really to rely on some deployment channel partners. And these are these robotic solution builders, so the equivalent of the smartphone developers. And here we've been working with companies of all sizes, right? So it goes from Trinity, a 20-people company in San Jose, California, using our tools to doing some high-mix CNC machine tending, to a company like Trumpf or United Grinding in Europe, which are like $5–10 billion companies, to very large multinationals like Foxconn, who are using our tools to doing electronics assembly and who are $200 billion companies, right? So our tools apply to the full spectrum of partner sites. And these partners will then go and take these tools, create their solutions, and deploy it at a variety of end customers. And here's the same story. These end customers range from small machine shops, 20 people, to very large factories, very advanced factories of companies, multinationals. Okay, so I spoke quite a bit of the theory and the strategy and how we're trying to create Android for robotics. But I didn't show any concrete examples, any real video. I promised you we would talk about real production development. So I'm going to hand it over to my colleagues to walk you through some of these real case stories where some of this technology is today, not in the lab, not in a marketing video, not at a trade show, but also in a real production environment.
So let's talk about Trumpf, one of our very early adopters, very great partners. Just a quick introduction. They're a market leader in machine tools and a lot of other sectors, but today we really want to focus on the machine tools part of it. So they basically build solutions throughout the whole value chain in sheet metal, from starting with laser cutting machines, via punching machines, through bending, and then also welding these parts together. They're a huge developer that is very, very innovative as a company. And they have roughly $4.5 billion in revenue. So super interesting partner. And for us, actually, this is exactly where domain expertise matches our AI and robotics expertise. And that's exactly where the value for end customers is created. I want to start with a quick video to show you about the use case that we look at today. Looks great, doesn't it? So that was actually a video done by the Trumpf product team 1.5 years ago to basically show the vision that we wanted to create together. And I think reliable separation and then autonomous sorting is actually the keyword, and I'll go back to that later in a little bit. Unfortunately, reality oftentimes looks a bit different if you look to a machine shop actually in sheet metal. The sorting part after a laser cutter is often done very manually. You have big piles of scrap in some corner, so we have a way to get there actually to see this clear and nice vision of actually autonomous sorting in the end. So how do we together with Trumpf actually do this? So the first thing is that Trumpf actually set it up in a two-step approach, right? The first thing, we separate the parts from a skeleton in a product that's called this Trumpf Sortmaster Station. That's done by Trumpf separately. I invite everyone to look it up. It's actually a super interesting product in itself. And after the parts that are being cut out of the big sheet metal are then separated from it, then we come into play. And that's actually the sorting afterwards onto pellets to actually feed the next downstream process. And that is done actually with the Sortmaster vision, that's in the end powered by Intrinsic Intelligence. So what are actually the challenges here? First one, you have a lot of different parts in different sizes, from very small ones to very large ones, and also very, very small lot sizes, because you want to optimize actually to minimize the scrap that goes out of the Sortmaster, out of the laser cutting machine. Secondly, they're positioned on a very large surface, right? They moved after the separation process, so we don't know exactly where they're lying. And they actually can partially overlap afterwards. And all of this actually happens in very, very challenging lighting conditions. So it's super hard to actually see the parts afterwards. For traditional perception, this is actually an impossible task. So that's exactly where the first building block, comes into play, which is what Simon talked about already, the intrinsic vision model. With this, on the right side, you can actually see a video of the Sortmaster vision in action. We detect all the parts that we then afterwards want to sort onto the pellets. If we've actually detected where they are, the next big challenge is actually to pick them up. And given that we talk about very, very small parts up to very, very large parts, this is not only a challenge in software, this is also a challenge on the hardware side. So Trumpf, our partner, came up with a very, very flexible gripper. And together with our grasp planning, this is actually then making this happen. Afterwards, the other building blocks, of course, moving the parts where they are and then placing it onto the pellets also come into play. So this is actually the setup. Just quickly, on the right side, you see the parts lying on a large surface. We have 4 cameras on top to detect them. We have a large Fanuc robot in the middle. We have a very highly flexible gripper to actually pick up the parts. And then we have pellets and maybe sometimes even bins to basically place them afterwards. And all of this, if we've solved it on a technological level, it's great. But we also want to make it usable, right? So the next thing is that for this whole process, even down to a lot size of 1, no robot reprogramming is needed at all. It's completely integrated into the whole Trumpf process of basically creating nestings for laser cutting machines. So it's done with a very, very easy to use HMI operator for operators. And actually this enables us in the end to automate high mix applications. So on the left side, you see actually a video of a trade show 1.5 years ago, but this is actually currently running in production sites as of now. And if you're interested in it, stay tuned. There's a couple of announcements coming throughout the year, and just approach me if you have any questions. And with that, I'll hand over to Henrike for another partner, another application.
Let's look at another real-life example. And this time we're talking about one of the smaller solution builders. So Simon mentioned we have small ones, we have big ones. So this is definitely a small one, based in the Black Forest in Germany. And I'm going to share a little bit about what they do with us. So first of all, MartinSystems is what they call. They're a small integrator based in the Black Forest, as said. They're a family-owned business, 2nd generation, 3rd generation is already lined up. They have 50 employees. roughly 10 million annual revenue, and they actually have two companies. So one called Martin Mechanics, which is more focused on really custom solutions. So the typical system integrator business where you really build one-off solutions. But what we are mostly interested in is their sister company or a second company called MartinSystems, where they really focus on productized solutions. So solutions as a product that are standard and that can be sold and scaled to many end customers. And here you see a little bit of their product range. So they do industrial, they also do mobile robots, really ranging from tending to sorting to palletizing applications. And the big thing where they're interested to work with us is really unlocking this high mix use case. So something that Christoph and Simon already talked about, it's really about this getting eventually to this like lot size 1 that small machine builders can actually automate their production with us today. Yeah, and the first use case we're doing with them is CNC machine tending, and you see an example here of what we exhibited with them at Automatica last year. Yes, this is a trade show video, but this is also happening on the shop floor. We unfortunately don't have a video yet, but it's coming soon. So this is something what we call the Max AI cell, and you see there is a drawer system where the operator can basically load the cell, and the parts don't need to be fixtured. So that's the first thing. We're using our advanced perception models to do a pose estimation of the parts. So very reliable 60 pose estimation. You can see the camera here, the wrist camera taking 3 images, what we call like a multi-view perception process. And then when we have perceived the part or have located the part, we can then do a grasp planning, and that's actually also happening automatically, happening on the fly. So none of this is being pre-programmed. Then we grasp the part, as you see, and then we do an automatic collision-free motion planning. Also, again, not pre-programmed. So we're using our digital twin technology to set this all up in simulation, try it out in simulation, and then really plan the path on the go. And I think for everybody who is coming from traditional automation, you guys know, usually these paths are really like taught manually with many waypoints, and it takes a lot of time to optimize these paths. This is all happening automatically. And I think, you can imagine with these 3 capabilities, or even there's the last one, which I almost forgot, like the insertion. So we're using a force-based insertion process, which means we're not just dropping the part in the vise, but we're really like inserting it with a sense of touch, as we call it, to really make sure it's inserted the right way in the vise. And if you combine all these AI-infused capabilities, you get the idea that we could really like tackle this high mix use case. So imagine a small machine shop who has like batch sizes of, 50 to 500 parts, and they would currently need to call their system integrator every 30 to 60 minutes and tell them, please reprogram the robot for me because I have a new part. With our technology, they don't have to do that anymore. So they can basically just upload the CAD file of a new part, or if it's a raw stock, you just insert the dimensions of the part, and then the robot reprograms itself, adapting to that new part. And that's a game changer. I think that's a completely new way to automate use cases today. And we're doing that by also providing a very intuitive HMI, so the operator can use the HMI to upload the new CAD file of the part and interact with the system in a very easy and intuitive way. And let's take a look in the future. So what I showed you is where we are at today, what we call like the high mix operation baseline. So an operator can upload a new file, doesn't need to involve the system integrator at all. But there are new things that we are planning on our roadmap to actually get to a future, what we call like lights out manufacturing or lights out automation. And the next step to get there is actually to queue several jobs. So you can imagine today you can set up like one job and go from one job to the next, but it would be so much better if you can already queue a couple of jobs after each other, do that maybe at the end of your shift, and then let the system run over the night shift. And then after that is what we're tackling is like automating several operations. So right now we're talking about like, doing the first operation of a part, doing the first operation in the CNC machine. But the next step would be doing several steps of automation, several steps of manufacturing, like milling, after each other. And for that we would add like a flipping station. So you all know that you have a part, gets inserted into the vise, gets taken out, gets flipped at some form of flipping station, and then reinserted into the device for the second operation. So that's already getting us closer than to a full lights out setup. But the full lights up setup would then really be you have, you can handle any kinds of parts, you can queue different jobs after each other, and you can also run different operations. And you can imagine that's not only, that doesn't only need you to upload the CAD file, but also to do an automatic finger change, an automatic jaw change, to really handle these different parts one after each other. Yeah, I think with that, we're at the end of the presentation. So thank you guys all for joining. It's been great. Thank you guys.